One of the notions that would be central to future developments in this course, and also for those of you who will take the second installment of this class during the spring semester, is a notion of a sequence. So during this lecture, we're going to introduce sequences and then talk about convergence of a sequence. So what is a sequence? We can give it the following definition. A sequence is an ordered set of infinitely many real numbers. So something like this is a sequence. So let's give a couple of examples. So typically, if we're describing a set, then we put elements of a set in the brackets. So let's say, for example, something like this: 1, 2, 3, 4, 5, 6, etc. This is a sequence. Something like that. 2, 1, 3, 4, 5, 6, etc. is also a sequence. But it is a different sequence than the first one. So let's label these examples as A, B, but it is a different sequence. Than an A. Because not elements are going to be in the same order. So if I'm saying that sequence is an ordered set, that means that the order of elements is important. If at least two elements are going to switch their locations, then that means already that you're getting a different sequence. Another example maybe something like this: 2, 1, 4, 3, 6, 5, 8, 7, and so on. Also a sequence. But again, this is different from A or B. Right? So even though the elements that we are using in both cases are exactly the same, those are natural numbers, then nevertheless these sequences are all different. Okay, so far the sequences that I gave you example of are all sequences. So A, B, and C. Are sequences of natural numbers. And if they are sequences of natural numbers, they're automatically sequences of real numbers because natural numbers are real numbers. Let's look at D. Actually, one important thing here is that in all three cases, in fact, whenever I talk about a sequence, in all cases I'll have to specify infinitely many elements. So that means that in your specification, it has to be done in such a way so that it is clear what all elements of the sequence are. You have to be able to prescribe or describe what all elements of a sequence are. So in the case A, it's clear that you just list all natural numbers in order. In the case B, it already is not so clear, but if I say that the first element is 2, second element is 1, and then sequentially I'm going to list all natural numbers starting from 3, right? And then I define my sequence fully and completely, because I gave you a recipe how to produce all elements of a sequence. Likewise, in the case C, you can observe that what I'm doing here is that I'm listing the first even integer, then a previous odd integer, second even integer, previous odd integer, and so on. Again, that means that I really specified the rule according to which I generate my sequence. Another way in which you can specify a sequence will be this. Well, actually, let me do something first, and then we'll return to what I was going to say here. So let's say in D, let me define a sequence like this: 1, minus 1, 1, minus 1, 1, minus 1, etc. So once again, in this case, I specified exactly how my sequence is going to look like. Always at every odd position, I'm going to have 1. At every even position, I'm going to have minus 1. So in that sense, we specified infinitely many numbers with alternating 1s and minus 1s. So D is also a sequence. E, let's try something like this: 1, 1/2, 1/4, and so on, right? Again, those are all sequences. And in that third case, in the case E, again, it seems that I specified exactly what is going on, right? Because what I'm putting at each position is going to be 1 divided by 2 to the power where this position of an element is, minus 1. Right, so in a position, at a position 1, I have 1, then I have 1/2, then I have 1/4. So if I keep going, I'm going to get 1/8, 1/16, etc. So in this way, again, we specified all possible elements of the sequence. And in fact, looking at all these, 5 examples, we can see that an alternative way to generating the rules rather than describing it in words or listing elements is to describe what exactly you're going to put at a given position here, what element you're going to put at which position, and to provide the relationship between the location of an element and the value of an element itself. So for instance, here at position 1 I have 1, at position 2 I have 2, position 3 I have 3. So an element of a sequence that I'm supposed to put, let's say, at the 6th position is 6. Element of a sequence that I'm supposed to put at the 15th position, in this case, is going to be 15. So that means that I can specify my sequence in the following way. I'll specify each element as a function of its position. So I can specify, so alternatively, rather than listing elements, I can do this. So in the case A, I can say that I have a sequence Sn equal to n, where n is greater or equal than 1, right? So Sn is then the nth element of the sequence. And in this way, I am specifying what each element of a sequence is depending on its index. So n is the index. Alternatively, again, or I can specify the same sequence in this way, just saying n, where n is in n. So as n goes from 1 to infinity, right, along all natural numbers, in this way I'm specifying a set, and I'm assuming that I put all the elements of the set in order. All right, sometimes also we will say Sn, n belongs to n, or Sn, n goes from 1 to n. All of these things will just mean the same thing. So in this case, instead of Sn, right, we're going to write n in n, or n, where n goes from 1 to n, right? All of these, in all of these different ways, I'm specifying the same sequence. Then in a case B, let's see what we can say. Sn, I'll have to specify separately, right? So in the case B, I exchange two elements, first element and the second element, I exchange their positions. So I can say this, S1 is equal to 2, S2 is equal to 1, and then Sn, starting from 3, right, I'm going to have exactly the same value as a position of the element. At 3 I have 3, position 4 I have 4, and so on. So then Sn is equal to n if n is greater or equal than 3. All right, so that's a sequence in B. In C, so in a case C, what we see is even numbers at odd positions and odd numbers at even positions. If we need to provide the prescription of how to compute an element as a function of its position, then we need a piecewise defined function. So we will say, in case C, that Sn will have a different value depending on whether n is even or odd. If n is odd, then we always have to put an element which is by 1 higher than the location, than a position of element, right? At position 1 we have 2, at position 3 we have 4, so Sn is equal to n plus 1. if n is odd. And on the other hand, if we look at the position 2, we see 1. At position 3, let's see, at the position 2 we have 1, at the position 4 we have 3. So then it's by 1 less. The value of an element in 1 is 1 less in its position. So n minus 1 if n is even. And otherwise n is any natural number, right? So this specifies a sequence uniquely. What was d? d is 1 minus 1, 1 minus 1. Can we see how Sn depends on n in the case d? Well, how do I get minus 1 and 1? Both of those are powers of minus 1, right? So if I take minus 1 to an odd power, I'm going to get minus 1. If I take minus 1 to even power, I have 1. So what that means is that when I'm looking at an element at the first position, I want to raise minus 1 to an even power. When I'm looking at element at the second position, I want to raise minus 1 to an odd power, even power, odd power. So how can I take this into account? I can make Sn to be minus 1 to the power that depends on position. So at the first position, I want to see an even number. So how would I get an even number? Well, it's 2. Let's see. No, it's not 2. It's just n plus 1, right? So if n is 1, n plus 1 is even. So minus 1 to the even is 1. If n is 2, then n2 plus 1 is 3. That's odd. Minus 1 to the odd is minus 1. So by changing n, then I'm going to alternate between minus 1 and 1. And so that will describe a sequence in D uniquely. And finally, what about E? Well, in this case, it's easy to see that Sn actually is 1 over 2 to the power n minus 1. Right, because if n is equal to 1, I have 1 to the power, 1 over 2 to the power 0, this is 1. N is equal to 2, 2 minus 1 is 1, 1 half, n equal to 3, right, that's the third position. 1 over 3, 1 over 2 to the power 3 minus 1, 1 over 2 squared is 1/4, and so on. Again, alternatively, I will just write sometimes this minus 1 to the power n plus 1 in curly brackets, right? That would again mean the same thing. Or minus 1 to the n plus 1 and from 1 to infinity. Again, this means that I have an infinite sequence. In this case, 1 over 2 to the n and from 1 to infinity. All right, so those are a few examples. Actually, let's give maybe one more. Or before I give one more, let's talk about the following then. So what we observed is that we can specify a sequence by stating how Sn depends on n. So then I can think of Sn, so I can think of a sequence Sn as a function S of n. Right, so for example, in a case E, above, S of n is equal to 1 over 2 to the power n. So it's a function, and again here n is an element of a set of natural numbers. So S of n is a function from the set of all natural numbers, from n, to the set of all reals. Right? So either I prescribe this function by giving you the formula, or I prescribe this function by listing what the value of the function is for each n. So we can identify each sequence with a function from a set of natural numbers to the set of all reals. And now if you have a function, you should be able to graph it. So therefore we can graph a sequence. How can we do that? So let's use an example E again. Let's say Sn is 1 over 2 to the power n, n is an n, right? That's a case E. And the way to graph it, this function now is defined only on natural numbers. So then on a real axis, I'm actually not looking at the entire real axis. I'm just looking at all natural numbers. And I'm going to sketch or plot all points that correspond to values of S above each n. So Sn, S1 is going to be, actually this is not exactly E, so let's do exactly, so Sn is 1 over 2 to the n minus 1. So then if n is equal to 1, we have 1 over 2 to the power 1 minus 1, that's 1, right? 1 over 2 to the power 0 is 1. Then S2 is going to be 1/2, then 1/4, 1/8, 1/16, and so on. So the graph in this case is a set of infinitely many discrete points. So then thinking about calculus, right, so if I have a graph of infinitely many points, if the graph of a sequence is a set of points, then clearly I cannot talk about continuous functions, continuous sequences, or I cannot talk about differentiable sequences because there is no way here to take a derivative. All right. So let's hope that all of this makes sense. Let's look at another example. This is going to be F. Sequences can also be defined recursively. Now, this is something that you cannot do if you are trying to define a function of a real variable. So what are we going to do here? So for example, let's take S1 to be 1, and then Sn plus 1 is equal to, let's say, 2Sn plus 3. And this is true for each. You'll use a second prescription for each n which is greater or equal than 2. Can I then describe how my sequence looks like? So then, what is S1? S1 is specified, it's 1. What should be S2? S2, I will plug in S1 into the description for, well, actually, let me do it. Correct this. This is for n greater or equal than 1. So how would I compute S2? I'm going to compute it from this formula by plugging in S1. So then, if n is equal to 1, 2 times S1 plus 3, 2 times 1 plus 3 is 5, so S2 is 5. If S2 is 5, how do I get S3? From here, S3 depends on S2. So if I want to compute S3, n is equal to 2. And then 2 times S2 plus 3, that's 2 times 5 plus 3. So the next term is 13. Let's do one more. If S3 is 13, then what is S4? When I compute S4, n is equal to 3. S4 is 2S3 plus 3. S3 is 13. So 26 plus 3, that is 29. And I can continue like this forever, and I will be able to specify all elements. So this Sn is still a function of n, right? Because to each position n, I have a number corresponding to that position. But I will not be able to provide you with a rule, with explicit rule, which says if n is equal to something, then Sn is equal to something else. Because in this case, the value of the next term depends on what the value of the previous term is. So I have to follow this chain of computations, this recursive chain of computations, to figure out what the nth element is. So maybe I will not be able then to produce a formula for Sn, but as we will see later on, nevertheless, we will be able to still conclude certain things about the behavior of these sequences when n is large. All right, so let's see, G. Let's consider another recursive sequence. Let's say S1 is 2, S3 is 4, and Sn plus 2 is going to be equal to Sn plus Sn minus 1 if n is, okay, let's see, let me see, let me rewrite this actually. Sn is equal to Sn minus 1 plus Sn minus 2 if n is greater or equal than 3. And sorry, this is also nonsense, S2. All right, so can I reconstruct this sequence? Again, it is recursive because next element depends on previous elements. So if I want to list the elements of a sequence, 2 and 4 come in automatically because I know what S1 and S2 are going to be. Then what is S3? S3 should be S2 plus S1. S2 is 4, S1 is 2, 2 plus 4, 6. what is S4? It's S3 plus S2. S2 is 4, S3 is 6, so S4 is 10. So it should not take a lot of convincing to see that in this case, actually, what is going to happen is that each element is a sum of previous two elements. So then clearly at the next position, I'll have a sum of 6 and 10. That's 16, next 10 and 16, 26, etc. So again, we can easily define what is recursive, reconstruct what this recursive sequence is. H. Let's look at an easier case. Let's say Sn is equal to n plus 3 over n plus 1. N is greater or equal than, let's say, 0. Because in principle, nothing says that I have to start counting from element 1. Maybe I can start my index from n equal to 0. So what do we have? So then we have that S0 is equal to 0 plus 3 over 0 plus 1. That is 3. S1 is going to be 1 plus 3 over 1 plus 1 for 4 halves. And then S2 is 5/3, S3 is 3 halves, etc. So if we start listing out the elements, then the sequence Sn here is going to look like this. Then what I want is to check the following. So if you look at all those sequences that we have looked at so far, what I want to understand is what these sequences are doing when I make n bigger. The question is, would I be able to detect any specific behavior of the elements of a sequence as n increases? And let's look at the sequences that we have listed so far. So if I look at the sequence A, right here, is there a particular behavior of elements as n tends to infinity? Well, so we'll see that because an element is equal to its position in a sequence, its location in the sequence, then as I move along the sequence increasing n, I increase the elements, so as n gets bigger, the elements get bigger. So in a sense, by using our previous discussion of sets, as a set, the sequence is unbounded. And so, in a sense, I can even say that the limit of the elements of the sequence as n goes to infinity is infinity. Same thing for the sequence B, because the only difference between sequence A and sequence B is the first two elements. So if I'm interested in the behavior of terms of my sequence as n gets larger, starting from 3, both sequences are exactly the same. So the sequence B, in that sense, also kind of goes to infinity. Still the same with the sequence C, because what do I have here? I have that as n increases, again, terms of the sequence also would increase. Each term here is either n minus 1 or n plus 1, depending on at which position this term is located, right? Even or odd. But it doesn't matter, as n gets bigger, terms of a sequence gets bigger, so once again, the expectation is that this sequence goes to infinity. Sequence D, here we're alternating between 1 and minus 1. Then as n goes to infinity, there is no somehow specific behavior except the fact that you keep jumping between minus 1 and 1. So the sequence does not really approach any particular number. Yet what it does oscillate within specific finite bounds. It's never going to be greater than 1, and it's never going to be less than -1. And later on, we'll see that this behavior actually is of interest, so that we will describe it more precisely, this sort of oscillating behavior. Okay, what about the sequence E? For the sequence E, we see that if n gets bigger, then elements of a sequence will get smaller, right? 1, 1/2, 1/4, 1/8, 1/16. The larger is n, the smaller is a element of a sequence. So then we should be able to say that as n goes to infinity, then the elements of a sequence approach 0. They become infinitesimally small. How about the sequence F? So F was this recursively defined sequence. Well, here again, it stands to reason that just by inspecting the sequence, the elements of a sequence that we computed so far, it stands to reason that this sequence also is not going to be bounded, because what you're doing on each step, you're doubling the size of Sn, and then you're adding 3 for the good measure. So that means that each next term is going to be significantly bigger than the previous term, and so we should expect that this sequence goes to infinity. Likewise for the sequence G, and what about the sequence H? Well, here, what do we know? We know that top is getting bigger, right? Because the top is n plus 3. On the bottom we have n plus 1, so n is also big. So if we have a large number plus 3 or large number plus 1, really this is the same number. So as n goes to infinity, in this case we expect that Sn is going to tend to 1. And so what we arrive at actually is the fact that with sequences, just like with functions, we should be able to define the notion of a limit. So, for instance, by looking at a sequence like this, so another example, let's call this GHI. Let's consider a sequence Sn is equal to 1 over n is an n, or n is greater or equal than 1, that means the same thing. Then, if I list elements of this particular sequence, they're going to be 1, 1/2, 1/3, 1/4, and so on. And so then the conclusion, by looking at this sequence, an obvious conclusion is that as n tends to infinity, Sn tends to 0, right? So we want to say then, or we would like to say, in this case, that the limit n goes to infinity of Sn is equal to 0. Okay, so then in the case H, so likewise in H, we would expect that the limit, we want to say that the limit as n goes to infinity of n plus 3 over n plus 1 is equal to 1. Okay, so to make the notion of limit precise, we need to give an appropriate definition. And before I give a definition, let's try to express in words what exactly do we mean by limit. So let's ask this question here. What is meant by the limit? So roughly speaking, it's this. So what does it mean, for example, that the limit of Sn is equal to 0? It means that I can make Sn arbitrarily close or as close as I wish to 0. And how can I accomplish it? By making n sufficiently big. Well, similar if I'm saying that the limit of n plus 3 over n plus 1 as n goes to infinity is 1, what do I mean by this? I mean that I can make n plus 3 over n plus 1 as close to 1 as I wish, as long as I take n sufficiently big. So let's actually write this down. Limit as n goes to infinity of Sn equals to L if Sn can be made arbitrarily close to L by taking n sufficiently large. So this passes as a pretty good definition of a limit until you start digging in the following. So the following things are not actually as clear as they appear to be. So if I'm saying that I can make Sn arbitrarily close to L, what exactly do I mean by this? What does it mean that S is close to L? That has to be made precise. And what does it mean that I should be able to take n sufficiently big, right? And it's clear that if a limit is equal to some number, then I can make, just like I said, n sufficiently big, and then Sn will be closer to L than some prescribed number. But what does a sufficiently big means? How do I actually verify if something is sufficiently big? In practice is yet not clear. Well, so let's try to translate these different notions to a mathematical language, and then we'll be able to reconstruct this definition in a precise way. So I want to translate this statement to a mathematical language. So what does it mean, or how do we make precise this statement? Let me copy this from here. Oops. That Sn can be made arbitrarily close to L. Well, what is Sn? Sn is a number, right? L is a number. If I'm saying that Sn is close to L, that is a statement about the distance between Sn and L. Okay, so then this statement here I can rephrase in the following way. Given any number, let's say I will call this number epsilon, that number is positive, we can make the distance between Sn and L smaller than epsilon. Right, I hope you agree that that's actually what it means, that I can make Sn arbitrarily close to L, right? So if I pick any number, no matter how small it is, I can make the distance between Sn and L smaller than that number. Okay, so how do we compute the distance between two numbers, right? And referring to a few lectures back, what's the distance between two real numbers? It's the absolute value of a difference between these two numbers. So, given any number epsilon greater than 0, what can I do with Sn minus L? I can make Sn minus L less than epsilon. Okay? So that's a phrase statement number 1. Statement number 2 that I want to make precise can be made arbitrarily close to L. We figure this out by taking n sufficiently large. Right? What does it mean for n to be, n is sufficiently so what does that mean? Well, if I'm saying that something is sufficiently large, that means that I should be able to distinguish between things being large enough or not large enough. That means that there must be some threshold for n above which something is going to happen. So what this means is that there exists some number capital N, some real number capital N, such that if n is bigger than capital N, then something happens. Okay? So to recap what I just said, Sn can be made arbitrarily close to L, means that given any epsilon greater than 0, I can make Sn minus L less than epsilon. And saying that n is sufficiently large means that there exists some threshold number capital N, such that if I take n bigger than capital N, then something is going to happen. And so given these, let's now translate the definition of a limit. So let's go back here. Let's see how we're going to rephrase it. So I'm saying that Sn can be made arbitrarily close to epsilon, arbitrarily close to n, to L, sorry. What I need to do, I would need to select an epsilon, and I want Sn minus L to be less than epsilon. How can I make Sn minus L less than epsilon? Well, I need to take n to be sufficiently large. So that means that if there is an epsilon, what should happen? There should exist a threshold value of n, such that if n, the index, is larger than this threshold value, then Sn minus L, or the distance between Sn and L, or absolute value of Sn minus L, that this thing is going to be less than epsilon. So translating the whole thing into a mathematical language, what I'm going to arrive at is this. So definition of the limit. And this is going to be absolutely the most important definition in this class, because I'm going to use this definition literally thousands of times. The limit of Sn as n goes to infinity is equal L, and we're going to use our standard notation, limit n goes to infinity of Sn is equal to L if for any epsilon greater than 0 there exists a capital N in R such that Sn minus L is going to be less than epsilon if n is greater than capital N. Okay, so for any accuracy epsilon, I can make Sn closer than epsilon to L by doing what? By taking n sufficiently large, or n bigger than capital N. So given for any epsilon, there exists a capital N. If I make epsilon smaller, capital N is going to be bigger. I make epsilon even smaller, capital N is going to be even bigger, right? So the larger is capital N, the farther away I'm going to move along my sequence, the closer is Sn to L. In a compact form, I can write the same statement. And I'm going to use this compact form over and over again because, again, as I said, we're going to rewrite this limit, this definition infinitely many times. So in the compact form, limit as n goes to infinity of Sn is equal to L if for any epsilon greater than 0, right? This symbol here means for any. There exists, this symbol that I'm writing right now means there exists, an n, a real number, such that if n is greater than capital N, then Sn minus L must be less than epsilon. So at the end of the day, my statement definition in the rough form here, my definition over here, and my compact definition down here all mean exactly the same thing, except that the rough definition is not really a definition, it's just a motivation for a real mathematical definition. Okay, and so then in the next lecture, I'm going to discuss how you use this definition to actually prove that the limits exist and are equal to a particular number. So, for example, we know for this example, Sn equal to 1 over n, clearly the limit of this sequence is 0. Visually, right? It's clear that it is 0. But can we prove that this is the case? Yes, we can, as long as we can demonstrate that the definition of a limit applies in this situation. Same thing for this case. Next time we will show that we can actually use the definition of a limit to demonstrate that indeed this limit is equal to 1. We can prove this, we can demonstrate this, or we can show this. All of these statements that I just made mean exactly the same thing.